All right. Good time of the day to all of our participants joining from all around the world. Very warm welcome and sincere welcome again to Retina in Action, the smart photonic sensing for healthcare, automotive, and agriculture applications. My name is Ivan, and it's my pleasure to serve as your moderator for today and guide you through this insightful workshop. We're gathered here today under the banner of RETINA project, an ambitious European initiative that sits at the very frontier of photonic technologies. And but what is the vision that drives this project, and what are the fundamental challenges and opportunities that it can bring to us together? This is the core of our discussion today, and our focus is not the final results of this project, but on the essential foundations, the background, the motivations, and the compelling need for smart photonic sensing. We have assembled a brilliant set of 7 leading experts from our Retina consortium, and throughout this session, we will illuminate the unique potentials of the photonics to revolutionize 3 vital sectors: the healthcare by enabling new diagnostic tools for earlier and more accurate detection; from automotive by creating safer and more intelligent sensing systems for the vehicles of tomorrow; and agriculture by fostering the sustainable practices through precise monitoring. So the Retina is a European project that that combines 13 partners from across Europe, and you will hear from many of them today. The agenda today is packed, and each speaker will deliver a concise presentation, followed by a dedicated short live question and answer session. And I will facilitate this Q&A session. So you just need to submit your questions pushing the raise hand button below in your Zoom screen. And I encourage you, all of you, to be curious and engage with our speakers. So we'll hear today from IMAN, Xenomatic, Quest Medical Imaging, University of Vigo, Fraunhofer HHI, IMEC, and Photon Focus, partners of this project. And the journey of Retina begins with a clear vision, and there is no better person to outline that vision than our project coordinator. And this is my great pleasure then to introduce our first speaker, Julio Iyade Quintero, a researcher from IMAN. And Julio will provide us the strategic overview and set the stage for the deep dive into this project to follow. Julio, welcome, and the virtual floor is yours.
Hello, Ivan. Thank you. You can see my presentation, right?
Yes, you're all set.
Okay, perfect. Okay, yes. As Ivan said, thank you everybody for coming. I'm not going to spend a lot of time introducing myself. You can search me in LinkedIn if you want, or any questions that you can have, you can ask me through this email if I'm not able to answer all of them today. Okay, I'm here as the project coordinator of the RETINA project. The RETINA project is coordinated by IMEN, and specifically I'm the person in charge of coordinating all the technical developments that they are in the project. For those of you who doesn't know, IMEN is a non-profit private research center in Galicia in Spain. We are experts and we develop our main research activities in manufacturing, especially in the metallurgic sector, but we are more than 250 researchers, and now we have a lot of different research lines and a lot of different expertise. But as I said, most of them are focused here in the metal sector. Okay, so the RETINA project, right now, a brief introduction of the consortium. We are 4 research centers, 2 large enterprises, 4 small and medium size enterprises, one hospital and two associations. One of them is EPIC, that is hosting now the event. As you can see, we are from all over Europe, so we have a very diverse consortium with a very wide area of expertise. I wanted to start talking first about the funding opportunity that we took care of for the RETINA, because it's for me, in my opinion, it's a special topic. If you more or less know a little bit about the topics, funding topics in Horizon Europe, about the European Consortium, this is a little bit strange because it's a project that asks you to start in a very small development in TRL 3, and they ask you to mature it until TRL 6, 7 is not the usual things in these kind of projects. And okay, here's a little bit of the description, but the main idea that the European Commission wanted to exploit here and to force is to develop the new generation of photonic sensors and do it in a way not only academic but also showing the applicability in different sectors. So this is why we have a starting point in TRL 3 and we go to TRL 6, 7. Specifically in the RETINA project, what we developed were two different technologies. One related to LIDAR in photonic integrated circuits, and another related to microfilters to generate new generation hyperspectral cameras. Obviously, because we are in our day and age, we have to also add AI to the mix because as you all know, AI is always going to make everything better, arguably. So we also have to focus on how to use these sensors with AI. And for the validation sector, we chose these three. They are three very, very diverse sectors. My colleagues will talk more in detail about them, but basically, if you are talking about hyperspectral imaging right now, you have to see how this affects the agricultural sector because it's one of the main focus of this kind of technologies. If you're going to talk of LIDAR, especially solid-state LIDAR, you have to validate it and test it in the automotive. And we have healthcare because we think that the combination of these both sensors can bring a lot of potential to the healthcare industry. So, okay, why we choose these two technologies or these two technology focus? I cannot speak for the whole consortium, but from IMEN, when we started looking this topic and we wanted to develop these things, the main reason can be summarized in this slide. Arguably, the more used sensors right now in the world are vision sensors, are camera sensors. And if you stop and think a little bit about the camera sensors, what you can see is that the information that they provide you about a scene is basically the shape of the objects that they are in the scene and the color of the objects they are in the scene. And the shape is related to the object's geometry, and the color is related to the object composition, of the object material, of the object chemistry, all of these things, okay? So what the next generations, of course, there's a lot of potential of just using conventional vision sensors, RGB cameras or monochromatic cameras. And there's a lot of interesting projects developing what you can do with these sensors, but what is going to be the evolution of these sensors, how we are going to improve the sensor even further. Well, in terms of geometry, 3D sensors is the next logical step. And in terms of composition, spectral sensors. Why is this? Okay, so the vision sensors only give you the shape of the object. They basically transform a 3D object in a 2D image, so you don't have the real geometry of the object. There are ways you can calculate this geometry with the images, but you don't have this information. So the next logical step for the sensors is to find a way of acquiring this 3D information. And related to composition, this maybe is a little bit separated of our everyday understanding of how light works and how this sensor works. But the main idea is behind is the physics that how light is reflected by the objects. The light that is reflected by an object is depends on the atomic and molecular structure of this object at the end. Depending on the composition, you will have some wavelengths being reflected and other being absorbed. So even if we think about our eye, what the color is giving us is information about the composition. If you think a simple example of plants, if you see a plant that is green, you know that is a healthy plant, or you have certain information that it is healthy. But if you see the leaves yellow or even brown, you will see that this plant is not healthy. And this is related with the amount of wavelength and what wavelengths are being reflected by this plant. And this is because of the chemical composition of the leaf. So spectral sensors, RGB cameras only have 3 bands. They only acquire this spectral information in 3 bands, and the spectral sensors acquire this information in much more bands, so they can give you more accurate description of the chemical composition of what they are seeing. So they are the next logical step in the evolution of the sensors. Okay, so this is going to be a little bit explained in more detail for our partners, but the idea is once we selected, okay, we want to be part of this evolution of the sensors, and we want to research and focus our research in this new type of sensors that will give our systems better abilities to discriminate geometry and discriminate composition of the scenes. We have to see what's the optimal way of doing it. Of course, the optimal way of doing it will depend on your type of thing and your problem, the problem that you are trying to solve with these sensors with this instance. But I want to give you all a little bit an idea of how the main technologies behind the spectral, hyperspectral imagers and 3D sensors work, so you can understand later when our colleagues explain the developments that we did in Retina, why we selected the ones that we selected. With hyperspectral cameras, you always have a problem. You have a 2D sensor, you only have a sensor that goes like this. It has only 2 rows and columns, and you want to acquire 3D information, because what a camera, an hyperspectral camera gives you is an image, a different image for each wavelength that it captures. Okay, so you can see it as a simple image for a single wavelength, like this representation of a leaf, or for a specific pixel, you will have all the wavelengths that the imager can capture and all of the bands that the image can capture. So you see, you have at the end a 3D type of information, and your camera is only able to capture 2D information at a time. So we have to sequentially acquire, if we want to acquire everything, we have to acquire it sequentially. So there are scanning setups that they are the most common right now, that capture or one row at a time for all the wavelengths, or one wavelength at a time for all the image, or even one row and one wavelength each time that they capture. So they have to be scanning both in the space and in the spectrum. The way that we developed the retina sensors is not like this. Is in a technology called microfilters that I think Carolina from IMEC will explain a little bit more. But basically, we sacrifice a little bit of the spatial and spectral resolution, and we capture everything at the same time. So we think that this is better because we are able to capture video images, video sequences instead of static images, and it's easier to use and it's more intuitive for any system that is already working with RGB cameras. Okay, related to the 3D sensors that we are developing, this is the main three technologies that they are using right now to capture 3D information. I think that Rick for Xenomatic will explain a little bit. Sorry, Francisco for the University of Vigo will explain a little bit more about the LIDAR sensor. Is the one that we are developing. But I just wanted to give you an idea that there's not the only one, but is the one that is arguably the best for outdoor scenarios and for high resolution images. You have stereo-based sensors. You can see an example here. This basically what they do is they capture the same thing with two cameras, and with this they capture the 3D information of, sorry, the stereo images are this one, and the 3D information of this of all the scene. But the problem is you need a scene that is with a lot of texture and easily to identify each part of the scene, or you will have problems like here. This is an image that we take in a vineyard with a stereo camera, and as you can see, it does not have a very good precision. You cannot differentiate individual leaves and anything like that. Time-of-flight sensors use light, and they measure the time that it takes to be reflected in the scene, but they capture the whole scene simultaneously. So they are quite fast, but the noise that they have and the amount of background light that they are able to support is not very good. And finally, we have the LIDAR sensors. They also capture the distance information, sending a signal back and forth, but they do it 1 pixel at a time, so they have more concentrated light, they have less noise, and more immunity to the background. Okay, so as I said, for the LIDAR, we selected, for the 3D technology, we selected to develop a LIDAR, and especially we selected to develop photonic integrated, based in photonic integrated circuits. I'm not going to stop here a lot because Francisco will give you more information. I just want to show you the advantages that our system is going to have with respect of the state of the art. For the spectral images, the hyperspectral cameras that we selected, as I said, they are based in microfilters and pixel level filters, and Carolina will explain a little bit more. Again, this is the main advantages, just to introduce you to the technology, and my colleagues will give you more information. And the third technology that we had to develop was how to work with AI with these sensors, because most of the AI right now is being developed for images and for RGB images, color images, and there was not an application or a platform able to that let us work with hyperspectral images and with 3D images at the same time and take most advantage of the sensors being developed. So the third development is related to how to work with AI with this type of data, and is this Abraya platform that one of the partners, Abraya, have developed. Okay, so I don't know how on time I am, so I'm going to go quickly through the use case 1 and 2 because they will be introduced in more detail by my partners, by my colleagues, but you have here more or less all the information, and then they will give you the full description and the full information then. For the agricultural use case, unfortunately, we don't have anyone from ADVIT today, but IMEN is very focused on this third use case for the development of the AI models and the validation of the sensors. So I can introduce you a little bit what we want to do. The idea is to use these sensors that we are developing and validate that they are more useful than the state-of-the-art ones for three specific things that we want to do in the vineyard. We want to detect water stress in the plants. This is a big problem. Each year is a bigger problem. We want to give the plants enough water so they are healthy, but we don't want to give too much because water now is a scarce resource in a lot of regions, especially in the summer when you need to work to give the water to these plants. Then we wanted to show that with the spectral sensors you have a better chance to detect early any disease that the vineyard can have, and we selected especially this disease, grapevine tract diseases. And finally, one thing that is very important is to assess how much grapes, how much fruits you are going to have at the end of the season. This is important because you have to manage the resource of your vineyard well, and you have to make sure that you have enough people to have this and to estimate how much wine you are going to produce, or how much fruit if it's only for human consumption without making wine. Okay, so for the 2 minutes I think I have, I'm going to explain a little bit these problems, how are being solved right now, and so you see what the problem is. The problem is that for most of these problems, they have to be solved manually. Most of the times, what you have is an expert that knows about these things and goes through the vineyard trying to monitor how the vineyard is going. For water stress, for example, the most accurate way to measuring it is with the leaf water potential. You have to take one leaf from your plant, you have to put it in a specialized equipment that they will give you a quantitative idea of the amount of water that the plant has. Obviously, this is very resource intensive. You need an expert that knows how to use this equipment, and you have to take one leaf of each plant that you want to measure, and then calculate this. So most of the times, this is not done like this. This is done in an indirect method, where you have sensors through all the vineyard and you measure the soil or the atmospheric humidity, and with these indirect measures, you calculate the amount of water that the plants have. In a lot of vineyards, what you have is a mix of these two. You have you take a few direct method samples, and then you extrapolate with the indirect methods. What we are trying to do is refine the remote methods, the spectral index method ones. The idea is by measuring the amount of reflectivity that the leaves have in certain wavelengths, you have an idea of the healthy status of the plant. And if you have even more wavelengths to measure, you can even differentiate if this health status, if a plant is in a bad health status because they have a disease, or because they have a lack of water, or because they need more nutrients, or things like that. So the same applies to the GTD detection. You have a direct method that is just taking some samples to the laboratory, but usually what you have is an expert going through the vineyard, checking plant by plant, and being sure and detecting the ones that are healthy and the ones that are not. So what we are trying to introduce is similar to the water stress, using different spectral bands, detect when the plants are healthy and when they have some disease. And finally, for the harvesting forecast, what they do is estimate it also manually. They are going through the vineyard, they annotate how many bunches of grapes they have, and they do an extrapolation to the whole harvesting. Of course, what the state of the art is right now, and what the commercial, what the companies are trying to introduce commercially, is a vision-based technique. You just, instead of someone counting the bunches of grapes, you put a camera in some place and you try to measure this, but the problem is that the camera cannot give you the real size of the bunch. They can only give you an estimate size. So this is why introducing a LIDAR in our systems will improve this harvesting estimation. I think this is the last. Oh, okay. I have one last slide very quickly. Sorry, Ivan. I think I'm going out of time. This is more or less what my role is in the project. Besides the coordination, we work in the signal processing for the LIDAR and the electronics. And in the viticulture use case, we are in charge of the validation and the development of the machine learning algorithms. And that's it.
Great. Thank you very much, Julio, for this comprehensive overview and also introducing us a little bit into the first use case that RETINA is working on. So the message to everyone. After each talk, once again, we have a little question and answer session. So please feel free to unmute yourself if you have a question. You can also push the raise hand button at the bottom of your Zoom screen. And I pass you the board so you can engage with our speakers a little bit. So think about your question, and in the meantime, I'll ask Julio. Yeah, this is very exciting, of course, the agricultural use case that you already introduced. Can you think of more usages for the same systems in the domain of agriculture?
Yeah, we are developing them to work on drones over unmanned aerial vehicles and in-ground prototypes. So basically, wherever in every agricultural application that you can put a drone or you can put a ground vehicle, it is going to be useful. Of course, for the different plants, you need different algorithms. You still need to train your algorithms, but it will be as useful for a wheat or for whatever plantation that is not a vineyard, as long as you can put a drone over it or a ground prototype around it.
But so once the algorithms are developed for one type of plant, you can imagine it will be easier for any other type of plant?
Yeah, depends on the application. For example, for water stress is probably going to be true because you will work with the spectral information, and what this information gives you is the amount of chlorophyll and the amount of nutrients and things like that. So probably transfer learning, and this is only opinion, please, transfer learning algorithms will work well, and you will need less a data set with less size to adapt it. For other things that depends on the shape of the leaves and things like that, it may be more difficult. And the thing is, this scenario is very difficult. It's in outdoors, you don't control the illumination, and you have a lot of variability because even if you have the same vineyard, it can change a lot from one year to another. You have a lot of new things that can happen. So the systems that we are developing, only just that the hardware and the prototypes that we are developing, if we optimize them for agricultural use, only the hardware is going to be for sure useful, even if you cannot take full advantage of the machine learning that we develop there.
Okay, fair enough. And another question, maybe to provoke our audience a little bit also. So it's very clear now after your talk what RETINA aims to offer to our community of photonics experts. What do you think the rest of the value chain of that is today in the audience could help the Retina project with? What kind of partnerships the Retina project is open to?
Oh, I don't know who is in the audience, so I don't know exactly what type of companies or what type of professionals are there. But I will say that we try to limit the number of sensors here to just the ones that we are developing in the here at the Retina. That's not exactly true. We have more sensors in some of the systems, but we try to limit it. But obviously, data fusion and adding more sensors to the systems will always be beneficial. So if other sensors that can work well with this kind of applications are added to our system, will be good. Then we are focusing a lot in the development of the sensors because the resources are limited. So the machine learnings that we are going to develop are going to be very simple ones, just to validate that the sensors give you advantage over the state-of-the-art ones. So anything related to machine learning, AI, applied to this data will be good. We are working on the data sets, and as many of them that can be made public will be made public and will be available in the Zenodo account of this project. And so the researchers can try new and improve AI algorithms in this type of data, and get better results than us with this data.
Okay, one last thing. Is a Braille platform going to be available to external partners also
Yes,
to
for
test their
sure.
sensors?
Yes, I'm not sure if it's totally available right now, because I know we are the beta testers of some new functionalities, but for sure, Abraya will welcome any client that they want, or that they are interested in working in this platform, to do the labeling, to do the training, to download the models. They are working a lot in semi-automatic labeling of these data sets that is not always easy in this type of data, and things like that.
All right. That's very good. So, is there any more questions from the audience? Okay. If not, I suggest we thank Julio again for this introduction. And we transition to our second speaker, who will introduce the second use case within the Retina project. And this is Rick Pyson, the Senior System Engineer at Xenomatic. Welcome, Rick.
Hello.
And Rick will cover for us the automotive use case within Retina.
Correct. So, trying to share my screen. Can you see it?
Yep. So it's full screen now. We have
Yeah.
a few, we have this Windows.
You get rid of
Love
the
it to remove, but other than this, yeah, you're good to go.
Yeah, I'm trying to remove that one last window. That should be better. Okay, so thanks for the introduction, Ivan. My name is Rick Pazen. I'm system engineer at Xenomatics, and today I will talk to you about what we call LIDAR qualitative performance for ADAS application. So company, I'm trying to move on to the next slide. Yes. So I'm working at Xenomatics being partner in the Retina project, and we are a company working on sensor solutions, and also application development with these sensors. We are applying them in various fields, from automotive, road construction, industrial, and smart city. And let's say the role that we are taking in this project is more in this automotive ADAS sensor situation. Yeah, but we are doing many more things, but that's what I want to focus on today. We are based in Leuven in Belgium, and we have offices worldwide at different continents, the Americas, Europe, and in the Asian continent. we have local offices, and also we work with many resellers across the globe. So basically, you can find us almost anywhere across the world. Okay. So how are we supporting the RETINA projects? First of all, we are representing the end user for the advanced driving and ADAS use case. It started off by listing system requirements for functional integration of the LIDAR under development. We are also working towards the development of AI algorithms in this application, focusing on road user and object detection, really to see how applicable this new LiDAR is in this use case. Yeah. And maybe before doing that, we are looking into LiDAR fundamental performance testing. And that is what I want to focus a bit more on today in this presentation. Yeah. As I said in the introduction title, I want to say something about qualitative performance. So what do I actually mean with that? Let's say we can separate the performance of a LiDAR into two big categories, quantitative and qualitative. Quantitative is what I mean, like what is the range, what is the resolution? You can put a number on all these parameters. And I think in general they are quite well established in the meanwhile for others use case. Long range, especially in front viewing system, people want a long range on low reflective targets in any condition. So with a lot of sunlight, a very low resolution, a decent frame rate, but mainly a very large field of view. So I don't want to focus too much on that today. I think this has been introduced in the project in previous workshops. Maybe you can refer to that later on, Ivan. I don't know. Today, I want to look at the qualitative performance, and I'm going to highlight three situations. One is how does a LiDAR deal with a retroreflector? So like traffic signs or also reflectors on vehicles or like safety clothing. All of these are these are retroreflective, which means they return a lot of signal, which is not an easy thing to deal with. And very often, I have the feeling it's not much talked about in this LiDAR discussions. Yeah. Another one is standoff. So what is the minimal measurement distance? You do not only want to measure very long range, but at the same time, you also want to be able to measure very close by. You don't want to be blinded by an object very close by. And yeah, last topic is sensor fusion readiness. This is more related to also the second bullet I listed before, like the AI application and sensor fusion. So how ready is the LiDAR under development for this topic? So first of all, retroreflective target handling. Then I first need to introduce some technical aspects of optics, being ghosting and blooming. I think you have to look at the top right picture to show you or to explain what is ghosting and blooming. This is a fundamental phenomenon in optics, and usually in cinematographic fields, it's used for making very beautiful images. But basically, what it is that when you have a bright source somewhere in your field of view, this bright source causes like a glow around that source, which is called blooming or flare. And the other aspect that you can see is like it creates some kind of a mirror image across the optical center of your system, and this is called ghosting. So basically, you have blooming and ghosting. Why is this important? A LiDAR is, in essence, an optical system, especially if you have either flash LiDARs or 1D array scanning LiDARs. So the array is somehow imaged with an optical system with a lens, and this array is then scanned. And because of that, they suffer from ghosting and blooming, and they suffer in such a way that, for instance, looking at the scene below here, for instance, if you have a very bright source, and this is not a light source, this is a retroreflector. Why do I consider that as a bright source? It is because the light that we are emitting to do our measurement, it has to be so strong to be able to measure long distance on low reflective targets. But because of that, if you hit a retroreflector, a lot of light is being returned in the order of 100,000 times more than what you expect from a 10% target at a large distance. So you can consider this retroreflector, although you don't see it in the point cloud here, you can consider it as a very bright light source. That's causing a little bit of blooming. So if you look at the edges here on the left side around this orange patch, you see the edges, they are a bit blue. That's a little bit of blooming, which results in distance measurements right around that target, which are at the same distance, and they're kind of obscuring a little bit what is behind. What is more problematic is a ghost image that you can see here. So basically this, I'm assuming you see my pointer, by the way. Tell me if it's not the case. You can see ghost images in the middle of the field of view of this scene. And that's basically an object which is being perceived as at the same distance as the source, being the reflector on the left, but just in the middle of your view. And other than that, there's actually nothing else. So thinking about the ADAS application, you could decide based on this image that there's actually an object blocking the road, while in reality it's not there. So your autonomous system will basically detect this as an object and cause a brake for no reason. Yeah? That's, of course, in essence, it's not unsafe, but it will make it maybe unsafe for people behind you. And of course, you don't want to be driving around all the time and getting brakes all the time. Because I don't know if you know, but if you drive in traffic, the world is full of retroreflectors. And for that, I can show you this example image, which is an example we took with our LiDAR Xavia. You see here, there's a bunch of reflectors. You see here very nearby, there's these work signs, which are retroreflector. They're also across the street or on the opposite driving direction here. There are signs here, like an arrow and a stop sign. There's a speed sign here and an indication of work. So, and here is in a small bicycle indication sign. So it's full of reflectors, and if you don't properly deal with those reflectors, you get a scene that looks something like this. You see here, this is clear road actually, but what you see here is a blue area. So the color in this image represents the distance. It's a distance color coding going from blue, which is very nearby, to yellow, which is very far away. The white area in the back means nothing's being detected there because, as you can see, there's sky. So you see that basically there's some distance measurement here in this area, which is much closer by than what it is in reality. And this is basically a consequence of blooming of this very close retroreflector on the left side. Yeah? Right after that, there's another one, and that is being reconstructed a bit further away. And then here you have those signposts, and they kind of bloom all across the horizontal field of view, making you believe there's something, but in reality, there's not. The expectation is that an FMCW LiDAR is inherently immune to ghosting because, well, let's say every viewing direction has its own coherent state, and it will interact with itself only and not with light coming from another direction. But this is something we have to validate, and this is something we will assist with at Cinematics, comparing that performance of the LiDAR under development with, let's say, what we consider as reference system being our own LiDAR, LiDAR Xavia, which has this what we call advanced reflector handling built in. So you see the effect of the reflector handling here at the bottom. All these ghosting effects are basically solved for with our implementation. And in a very clever way, so without doing scene interpretation or anything, just fundamentally solving the issue. So this is something we will be focusing on in the testing of the LiDAR under development. The second topic I wanted to address very briefly is standoff. So as I said in the introduction, you don't want to only see objects very far away at a low reflectivity level. You, at the same time, want to be able to see objects very close by and actually going up to a very high reflectivity level. Again, imagine a situation where you have a front view LiDAR in a car. or on a vehicle, and basically there is someone passing by at a crossroads or at a zebra crossing, and that person has a retroreflective jacket, and it's, let's say, within a meter or something. You don't want that person to blind the system, because when you're blind, you don't know anything anymore. You could say there's nothing, or you could say I'm blinded, but how do you judge whether you're blinded or not? So standoff is a very important topic as well, also very often not talked about in LiDAR performance parameters. And also there we have quite some experience with testing. As you can see here in this example on the right, there's like a 10% target at about 10 meter, which is being detected. But at the same time, we have a retroreflective sign here, very close to our test device here. It's within a few 10 centimeter. And you can see it's important to be able to detect that one, but at the same time not being blinded very, very far away in the rest of the field of the view. Yeah. So standoff is also a very important item to deal with in the ADAS use case when talking about LiDARs. And then the last thing I want to highlight is how ready is the sensor that's being developed to do sensor fusion. Is it an easy transformation going from a LiDAR to, for instance, an RGB camera? Yeah, what do we have to take into account? Will we have to look at distortion levels in one system with respect to the other, and how do we have to align all of this? Okay, introduction of this sensor fusion need is the fact that I think in general, the ideal LiDAR would be considered to be an RGB camera with distance information per pixel. That gives you and the distance and the high resolution that you have with a camera, plus the color, which is basically like how we perceive everything. If your sensor perceives the things with the same color, you can rely on that knowledge to basically develop your application. Yeah. So yeah, we will assist in combining the LiDAR under development with RGB camera to either colorize the point clouds or to leverage the resolution of the RGB camera in the LiDAR data, and also to combine or to develop AI models on this combined system. Yeah, it's important to have then both systems synchronized, triggering, but also taking into account possible scanning motions from one system and the other, if you have a rolling shutter or a global shutter camera. So all of that has to be taken into account and is important for the application. I talked about the sensor-to-sensor alignment being the intrinsic and the extrinsic parameters to properly define that. It's important to make sure that the system that you're developing is also compatible with other existing sensors to basically build your full application based on that. Yeah. Finally, as I said, working on AI development based on LiDAR data and camera data. We're also looking into edge deployment of these models on a system and see what is needed for that. What kind of processing power do I have? And how do we keep the model lightweight to be able to do this on a low level processing unit? Yeah. So all these topics, reflector handling, standoff, and sensor fusion are qualitative parameters, but I would say as crucial as the quantitative requirements that are typically listed for a LiDAR. And we will be helping with that in this project by let's say using our expertise. And once the LiDAR being developed in the project is there, we want to basically get our hands dirty with it and test it for all of these topics to see how well it can serve the application. So that was it. Thank you for your attention, and Ivan, you can take over again.
Thank you very much, Rick. Very nice explanation about our automotive use case, and I'm sure our audience have heard a few interesting insights about how the LiDARs work. So yeah, please let me know or raise your hands if you have questions for Rick. In the meantime, I wonder myself, Rick, as mentioned by Julio, Retina is also working on the drone systems, and as you explained very well about the LiDAR requirements for automotive, are they the same for the aerial systems, such as drones, or is there much difference?
I would say I think what I listed is very specific to the ADAS use case. A retroreflector is something that's all over the place if you drive, if you're in traffic. Of course, if you're on a drone and you're doing aerial scanning, you're looking down, there's typically no retroreflectors like that. I think, yeah, so it's less applicable in that situation. Maybe, yeah, maybe standoff when crossing high buildings or high power lines or these kind of things is important. I would say maybe the third topic is more applicable, being the sensor fusion with a visual camera to colorize your data. I think that will help a lot in the aerial scanning.
All right. Another question I have is regarding the spectra that is used in this kind of LiDAR systems. So what is exactly the spectral range Retina is aiming to use, and why? And also, is there much of a difference regarding the eye safety and other kinds of aspects that might differ with this spectral range of the LiDAR?
I think this is more a question to Francisco, but I will answer it. So basically, this is because of the integrated photonics working on the 1500 nanometer range. The systems or the data I've been showing was on the near infrared range. How is this different with respect to eye safety? In 1550, you can emit quite a lot of power more, like a few, I think an order of magnitude more before hitting the eye safety limits. So that gives you a lot of headroom with respect to achieving a certain range. Of course, the downside is that you need to be able to provide that power. So basically also the power consumption of your system will increase because of that. But I think, again, Francesco can say more about this.
All right. Yes, we will indeed dive deeper into the LiDAR topic a bit later on. So if there's no further questions from the audience, I suggest we thank Rick again, and we move then to the third use case elaborated by Retina, and that will be introduced to us by Dan Haver, the research scientist from Quest Medical Imaging. Welcome, Dan.
Thank you. Let me turn on the audio as well. Nice. Great. Thank you for having me. I will be illuminating you on the healthcare use case on the RETINA project. I've been making this presentation together with Rochelle, but Rochelle has recently found something else, and now I will be presenting this to you. I am a research scientist from Quest Medical Imaging. We are an Olympus company, and we are focusing on fluorescence imaging systems. And the way this is working is you have a camera, you illuminate a tissue with light. Typically, the tissue has some agent that is fluorescent. Most of the time, this is consisting inside of the blood vessels, and that allows you to expose how the blood perfusion in a tissue is, and then you can make assessments on it. One of the important things you can assess with perfusion information is where a lot of blood is coming together is typically a tumor. So one of the goals, especially in this RETINA project, is to improve lesion visualization, or lesion is typically also referred to as a tumor. I want to first touch base on the user needs. What do you actually need before you are able to tell whether a lesion is a lesion? You want to have a very high spatial resolution of your imaging system. A surgeon may make an assessment, but you want to make a guided resection such that all of the tissue that is malignant will be removed. But it's not only a superficial evaluation, there's also some penetration depth that is required. You can imagine that a tumor may grow in various sizes. You want to scoop out at least everything that is bad. Third of it is the signal to noise ratio, which you want to have very high. If there is one part that is marked very well, but there are occult parts that are not so well detected, then they might develop into some unwanted additional tumors. So you want to scoop out everything that is there. And then lastly, you want to have a very high contrast of various tissues, because it's not only the perfusion that will eventually make a good surgery possible, it's also identifying other specific tissues that might be damaged if you only focus on the blood flow. Moreover, for retina specific, there's also the requirement that we want to even have a well-functioning system in the presence of obscurance, like a blood puddle on top of the skin. And then I have a very positive mindset, so I added in a very nice to have, and that would be if it would be able to do it intraoperative. So you need to have real-time information. Okay, to focus really on retina itself, retina has a very unique combination of sensors available or being produced. They are listed here. I will go into them individually in the later slides. In the later slides, I will make a showcase of the current state-of-the-art techniques and how they are used in healthcare. And then I will reflect on the retina-defined goal, which is detect and measure tissue lesions position, size, and shape, even in the presence of obscurance such as blood. First of all, I want to introduce you to shortwave infrared fluorescence camera systems. Traditionally, in fluorescence imaging, people are looking into the near infrared, which is about 850 nanometers. One of the agents that is typically being used is ICG. You can forget about the name immediately, but the interesting characteristics of this ICG is that it has one major peak of fluorescence at approximately the same wavelength as the illumination, but there is also a second peak, which is very low in intensity, but very high in contrast with the neighboring peaks. This allows for a very interesting technique, because a higher wavelength also results into a larger penetration depth. So you can see with a high contrast, with more depth, it's with an already NDA tested agent, but then the detection of this is one of the challenges which we will also face in the retina project, and that is mainly because you have to filter out all the signal that is very high, and also be able to detect at this very high wavelength. Next topic I want to touch base on is a short-range LIDAR. We had a very interesting overview on LIDAR, and well, I'm very glad actually I learned more about this by Eric just now. Short-range LIDARs are what is going to be introduced in the healthcare use case of retina. And there is one big upside, which is also a downside, is that it's virtually unexplored. This is great because everything we do will actually already be quite a breakthrough. I found this one very nice archive article, so not peer-reviewed yet, but it's a very good breakdown on the differences between stereo endoscopes and LiDAR cameras. Stereo endoscopes are focusing on the matching of two color images, and that will tell you some depth. Let me first tell you that depth is actually quite interesting of a parameter for fluorescence imaging, because you can imagine if you illuminate something and it's further away, that the time it gets back, it will also diminish some of the fluorescent, so you can correct for how the fluorescence image is different for the different heights if you know the height. So a LIDAR has been used in this case, and it's shown to be quite a lot faster. So going to the real-time approach will be very interesting. And since it's not in the visible range, it has also a better performance with low illumination cases and in the presence of blood, which for healthcare use cases might be interesting if you are considering endoscopes, for example. Furthermore, it doesn't matter how far you are, because the more advanced the LIDAR technique will practically be. But LIDAR is typically also in the shortwave infrared. And that might prove a challenge if you want to also do shortwave infrared fluorescence. So you want to have this regime in a different regime than what you are using your other sensors for. Now, lastly, I want to touch base on the shortwave infrared snapshot spectral imagers. We will also be having a sensor like this. Some work has been done on this. And I found this one example which explains quite nicely what you can do with it in a healthcare case. So they made a phantom, like a fake kind of skin, where they added 3 different materials. And what you can see is that the absorbance peaks and of the different materials that they are using are distinguishable. And that allows you to distinguish fat and water. And since tumors are typically built up out of fat and watery tissue, you can even inside the tumor see the heterogeneity. And this may provide more information if you want to surgically remove it. So this allows for very nice contrast overlays. So not only the perfusion will then be highlighted, but also other tissues in this case. But since shortwave infrared also scatters on all the tissue that it is bouncing into for having a deeper penetration depth, it will also have a little bit of a blur and therefore decreased fidelity on the mapping. And that might prove one of the challenges. Then I want to reflect on how these techniques can be combined to reach our goal. I state our goal with a little bit of a visual reminder here. So I reconstructed these goals in an earlier slide into very direct measurements. You want to have high spatial resolution, large penetration depth, high signal to noise ratio, high contrast of the various tissues, and you want to be able to do it even with obscurance. And I think with the combination of these 3 techniques, you tackle actually everything. So I see quite a good promise in the healthcare case of the RETINA project. And I'm not sure if I'm already past my time, but I have one backup slide. I'm looking at Ivan, but I can't see Ivan actually. Yes, okay, good, nice. Then I can talk about AI because my job is AI actually. I did it in a hidden mode. Okay. AI and healthcare are quite interesting combinations, and they are quite widely used, but typically AI is now used on pre-operative approaches like MRI scan, PET scan, CT scan. Large data sets are not really publicly available because of privacy issues. And if you want to have a ground truth, typically you have either a surgeon assessing the tissue, or you have to do histology, which is essentially you cut out some part of the tissue and then you look afterwards at the tissue, whether actually some different tissue was there. So this proves actually all to be quite tricky challenges for intraoperative approaches. But I think with RETINA project, we have such a unique set of different approaches, like you have both structural and also functional data on the same tissue, which allows us to generate new approaches. And the approaches will therefore already be state of the art, since this combination is not existing yet. I have some ideas on that. I think this is a bit beyond the scope of today's presentation, but I would be very, very happy to elaborate on this over mail. Thank you. That was it for me.
Okay, thank you very much, Dan. Indeed, an excellent presentation on this use case, and it was very interesting indeed also to hear about your role in this. So this is now open also for questions from the audience, but I'll start myself. Dan, I'm wondering, so since you are so much focused on the AI and this dataset analysis, what kind of support you could imagine for yourself from not only from the Retina partners, but also outside from the community that is now in the audience and potential end users of this kind of systems? Is there any particular data set you would really welcome to have in order to train your algorithms?
That's a good question. I am actually not fully aware of what is out there in view of the data sets. I know there is this hyperspectral big data set, which is, I think, open source, which is already quite helpful if you want to work on hyperspectral imaging. But as far as hospital maintained data sets, I'm not aware what is out there. So I would be very happy to collaborate on anything that has large amounts of data. So if someone happens to have a large amount of data, I'm open for collaboration. Yeah.
All right. But would it only cover, this kind of endangered tissue, the type of data sets that you have shown, or would you also be interested in other type of medical data, maybe covering another similar application within the medical domain?
I think other tissues might also be very relevant, especially if you are looking into hyperspectral imaging. Like you can really distinguish the different kinds of tissues. So that could also be bone structure or, mostly superficial. Moreover, Quest is very experienced on assessing perfusion data. So if someone happens to have or be involved or know something about a very big perfusion data sets, then there is also a big likelihood that we want to collaborate on that.
All right. Okay, well, thank you very much, Dan, and I'm afraid we need to catch up on the timing now. So I will invite now the next speaker of this session, and that is Francisco Luz Soares, a professor of University of Vigo. And Francisco will help us with a deep dive into the LIDAR technology based on PICs. Welcome, Francisco.
Thank you very much, Ivan. So my name is Francisco Soares, and I'm actually associated to University of Vigo, but I'm also the CTO of a Spark Foundry, which is a foundry for 3-5 semiconductors, recently started in here in the city of Vigo in Spain. But today I'll be in the capacity of the University of Vigo, and I will discuss here the activities that we've been doing on integrating a LIDAR on a PIC. This is a bit the outline. I'll explain a bit the FMCW LIDAR. It is a bit different than the time of flight. In the time of flight, you send a pulse out and then you measure how long it takes to come back, and then you can use a time to digital converter to do that, and that's what most commercial available LiDARs, they use that, but it has a bit some drawbacks, and in this project we'll focus on frequency modulated continuous wave LiDAR, which is FMCW LiDAR, and I'll explain a bit just briefly how it works, and yeah, that's it, just to have that out there, and there's some advantages that it has. And then I'll go into the specific implementation of this LiDAR that we are doing here in the RETINA project. And then I will show the current designs that we have, that we are currently fabricating, that target some in the long range. We hope to get around 100, more than 100. Actually, the target of the project is 140 meters. The detection. So what is free FMCW LIDAR? Well, a FMCW LIDAR, it's actually, if you know a bit of optics, it's quite similar. So we have here, which is what we call an interferometer. So you have a light signal, you split it 50-50, and then you combine it again in a combiner, right? Here in this combiner, there will be an interference because the light from the upper part and the lower part, they will interfere with each other, which means that the phase needs to be correct and everything. So if these parts, they are equal, then of course, if you change the wavelength, you have a tunable laser. If you change the wavelength and you measure how much current you're getting here in the detector, you'll just see a flat line because you will not get any change in the signal. However, what happens if you make one of these parts longer? Well, what happens when you make one of these parts longer? If you now change the wavelength, what happens is your balanced detector signal is going to change from constructive interference to destructive interference, and that's what you see here at the output. And that is because here, this long path, I hope you guys can see my cursor, hopefully, but in this long path, because you know the wavelength has an actual, it's a wavelength, so it's a distance, and so the phase here at the 50-50 combiner is going to change from 0 degrees to 100 degrees, and that is then from constructive to destructive interference. So you'll start to see here this destructive interference. And the period of this destructive interference, there is a formula for that. And that's this formula here. It tells you how much you need to change the wavelength to go from, well, to have a full circle of interference. And if you can then calculate how much you have. For instance, if this length difference is 1 meter, and you're talking here about air, because, you know, I'm showing here, this is like how we describe in the photonic integration concept, but this can also be, let's say, in a free space optics, this always happens and things like that. So it's just characteristics of light. For 1 meter, this is going to be, this period is going to be 1.2 picometers. And if you translate that to how much in optical frequency that is then 150 megahertz. If you go to a delta L, which is a length difference, which is 10 meters, then it's 0.2 picometers, and that's 50 megahertz. And then you can go all the way up to 100 meters. If you have 100 meters, then that change is going to be 0.012 picometers, and that's roughly 1.5 megahertz. But, you know, for these very long lengths, the frequency will start to approach the line width of the laser. This line with the lasers, typically they have a line width, right? But if your length is very long, then this period is going to change, is going to approach the line width of your laser. So that is that's actually the definition of the coherence length of a laser. That's how you define the coherence length of a laser. Now, what does the FMC LIDAR do? The FMC LIDAR, in essence, what it does is you don't know this delta L, but you would like to characterize what is this delta lambda, the change to go one period here from constructive to destructive to constructive interference. If you know that delta lambda, then you know the distance of your target. And that is basically what you do in an FMCW LIDAR. So in a FMCW LIDAR, the tunable laser, you're going to change the frequency, and you're going to ramp up, and then you're also going to ramp down. That is to get the Doppler effect. So you can determine whether your object is moving or not because of the Doppler effect. So if you're changing your wavelength to longer wavelengths, and then you change it again from longer to shorter, you can capture the Doppler effect, and then you can know whether your target's moving or not. So in an FMCW LiDAR, you're applying this triangular waveform, which is actually you're changing the wavelength of the laser, and based on the distance that you would like to scan here on this formula, you can know how much change you need to have, because you know, let's say if my target is at 100 meters, I know that I have to sweep the laser at least by 0.012. If your LiDAR system designed for 100 meters, you need to at least 0.012. So you're going to apply this triangular waveform, and then here you'll see, you'll have here, as you change the wavelength, you'll get this constructive, destructive interference. And then in the detector, you're going to sample that, and then you're going to do some signal processing, and then you can extract the delta L, which is going to be a function of the chirp and the sampling frequency and so on. So basically, this is the FMCW LiDAR concept. So you don't know what is the distance of object, but you're trying to measure this period, because this period is the period to your target. And if it's a short period, then your target's very far away. But if it's a long period, then your target is very close. So that's basically the thing, the FMCW LiDAR concept. And then with the ramping up and ramping down, here you're capturing the Doppler effect. So in essence, on this signal, you can do a Fourier transform, and then you can retrieve the frequency, and the frequency is related to this delta lambda. But if your target is moving, then instead of having one, you're going to have two signals, and then you know, oh, my target's moving. So, and the difference between these two is going to tell you what is the speed that it moves. And this is the FMCW LiDAR concept. It has many, several advantages over regular time of flight. For instance, it is a coherent system. A coherent system means that if I get here light from a different source, it's not going to cause interference here in the detector, because it's not coherent with the light coming here from the laser. So basically, the laser, your laser, it's going to interfere with the signal from the target. So if there is another signal that's coming from a different source, it's not going to affect your signal. So that's basically the FMCW LiDAR, and this is the system that we would like to integrate on a chip. The key components here is the tunable laser, where you need to apply this triangular waveform, and the balance detector. And of course, then also the passive elements, the splitters and combiners. So this is, let's say, the building blocks that you need to make an FMCW LiDAR. And yeah, that's basically how it works. Now we move on to the implementation that we have here in RETINA. So in RETINA, here on the left is shown the type of implementation that we will have. We will have here an indium phosphide chip, which will be fabricated by the Fraunhofer Heinrich Hertz Institute, and we will hear more from them later. We have a tunable laser, and then we divide it into multiple waveguides. And then each waveguide is going to have a grating coupler. A grating coupler is the device where the light comes in from this chip plane, and then these gratings make such that the light is exit to the bottom of the chip. So the light is radiated out of the waveguide. And here in the bottom, we have a lens, a commercial lens. The whole system needs to be designed so that it matches that. And this lens will collimate the beam because we're talking here about waveguides which are very narrow. So the light, when it exits the grating coupler, it's going to diverge. So we need here a lens to collimate the signal so that it can go to the target without, with the smallest possible divergence, meaning that the power you focus on the target and then you get it back and reflect, and then so that you can hit your target with a lot of optical power that later you can detect. And then the light reflects off a target, which would here be on the bottom, and then it comes back through the same path, and it's going to focus on exactly the same grating coupler. And then here, this grating coupler is going to go here to the balance detector, and it's going to interfere with the laser. And this is one, let's say, 1 pixel of our LIDAR system. And by changing this tunable laser across a long wavelength range, we can sweep the direction from going to one direction to another direction. And we have here multiple of these systems in one chip, and that is then how it, this is then basically the chip that we're currently designing. You notice here that there is no collimation here in the direction of the propagation of the in this longitudinal direction. That is because we're aiming here to have a long grating, and if you have a long grating, then we have a large light spot, and that can have a small divergence. And you see here as you see here, this divergence angle, when you go to a very long grating length, then it's going to be very small. So it's enough for you to send the light a long distance. Whereas here in the other direction, let's say transversal to the chip, here the light in this is a cross section across here one grating coupler. The light exits the chip, and then it goes to the lens, and it is focused then to the target. And this is basically the LIDAR concept that we're aiming for in RETINA. We have designed the whole system. We have designed this whole system, and we have also designed the grating couplers. And these are very shallowly etched grating couplers, meaning that the light here gradually starts leaking out of the grating coupler. And we've designed the edge depth to measure for a 30 nanometer edge depth. We can have a grating coupler length that can go up to 1 centimeter. And that is what we need to have in order to reach the 100 nanometers, target distance. If we etch deeper than 50 nanometers, then the light starts going out, let's say, at 5 millimeters. So we also designed we simulated also how much field of view we can get, which is actually not much, but 12 degrees, but we can change that a bit later with design by changing the grating period and etc.
Francisco,
and then
ask you to,
yes.
I'll ask you to wrap up, please. Yeah.
Oh, okay. So this is the we've designed the systems, and this is the last slide I'm showing here. These are the current 3 designs that we are currently fabricating at the Fraunhofer Institute, which is a partner of ours. So we've got this is a long range where we aim for a distance of more than 100 meters, and we have the short range where we have a wider field of view. And yes, but it's a less distance. And these are quite relatively long chips, which we had to do mainly for not reach the 100 meter case, the 100 meter targets. That's basically it. I'm sorry that I went a bit over time.
That's okay. That's okay. It's a very exciting topic. Thanks a lot, Francisco, for this deep dive into the design and technology of the FMCW LiDAR. I saw there was actually one question from the audience. Steven
Yes.
Theis from IMEC. Would you like to unmute and ask a question? Not sure if Steven is still with us. In any case, in the meantime, I'll ask Francisco. So you've shown that, of course, FFCW technology is interesting because apart from the distance, it allows you to see the speed of the object. It wasn't clear though. Can you really see the direction of the movement of the object, especially like if it's moving towards you or away from you? Is it clear from the data you obtain?
Whether it's moving clear way. Yeah. No, for that, whether it's moving away from you, yeah, you could of course differentiate the different flanks. You know the triangular waveform that we need to apply to the lasers, right? So if you go on one flank, that's actually when it's going one distance, and then the down flank is the other distance. But to differentiate whether this frequency and that frequency, whether it's the way, no, that is something. Yeah, that is. I don't know. I don't know. Yeah, you would have to differentiate between the two flanks of the triangular waveform. Yeah, that's actually a good question. I would have to check and see how that could. How that we could distinguish that, yes.
Perfect. I'm happy it was a useful question then. All right, so this is something also to discover.
I'm sorry, just one comment. We were talking earlier about the advantages of 1550 with respects to the 900 case. So in this project, we've aimed for 1550 nanometers LiDAR, and usually, you know, one of the reasons is because it's a bit eye safe. It's a bit eye safe, so that means you can inject lots of power, you can measure longer distance. However, there is a bit of a problem with humidity, water, so you have more water absorption than at 900. But then, as Dan was mentioning, at 900 nanometers, which is the other wavelength which is of interest, which we could also integrate everything on chip, there we have problems with interference with the other detection systems, which is the how do you call it? I forgot actually how do you call it, the luminescence with the other sensor systems that
yeah, the photoluminescence.
the photoluminescence
imagers, no? Okay.
Yes. So they usually work in that range. So for the medical case, you would have some problems there. But there's always this discussion whether 1550 and 900, and it's a bit of a debate on the thing. But we are in the world of LiDAR, but we are doing the 1550.
Okay. Well, very well explained. Thank you very much, Francisco. So with this, we thank you again, and we move to our next speaker that I think will also follow up on the same topic. Axel Schöne, the Deputy Head of Department at Fraunhofer HHI, will follow up on Francisco's discussion and tell us more about the indium phosphide peaks involved in these LiDAR systems. Welcome, Axel.
Thank you, Ivan, for introduction, and good afternoon, everyone. Yes, as Ivan already introduced, I'm Axel Schöne from the Fraunhofer HHI in Berlin. I'm the deputy head of the indium phosphide photonic foundry group, and I'd like to talk more about the PIC we have been manufacturing. So basically, speaking about Fraunhofer HHI, there are 75 institutes across Germany and also in other countries. But in our institute, we have got a budget of more than 40 million euros. We are more than 900 people and above around 80% self-financed. And this institute is comprised of several departments. One of the largest are the video compression or dealing with video compression. The other one is dealing with photonic networks and 5 or 6G networks. And we are working in the indium phosphide and hybrid PICs department. So we are offering solutions up to 145 gigahertz for terahertz applications, for any kind of sensing applications, quantum computing or QKD components, for example. And that's why we are here. So we are offering PICs for a sensing application in the framework of RETINA, so-called LIDAR PIC. Let's talk about our foundry service. So if you've ever heard about TSMC, we are like TSMC for indium phosphide, but we are just 10,000 times up to 100,000 times smaller than TSMC. But we are vertically integrated, so we can manufacture PICs, we can cleave them, we can do all the backend processing, and we can package them. And that's of interest within RETINA. So basically, everyone is able to use the PDK, the process design kit, to design a PIC. There are some softwares supporting the design flow, simulation software, design software. And this PIC, we saw already the principle proposed by Francisco, was actually designed with the off-the-shelf building blocks we have. On the right-hand side, you find some images. What we offer or what we have in our PDK is just a selection. There are some modulators on top left. There's a DFB, there are active components, emitting light. There are detecting components like photodetectors, balanced photodetectors, high-speed DC photodetectors. There are gratings, especially those gratings, or there's an adapted form of the gratings used for this project, but for the sample grading lasers, these are off-the-shelf components. Right, and we can also couple light in and out with low losses using process converters. We put this LiDAR chip on a dedicated wafer run, so we produced a couple of them on a single wafer, or you can actually scale it up. That's why we are here. So we have multi-project wafer services. We can just test a prototype PIC, but if you're satisfied with that prototype PIC, you can ramp it up. You can go for a couple of 100 wafers, for example. And this offers you the options for technology adaptation. You can have individual coding. In our case, we did not need that coding, which is also an advantage because it's faster. We omit steps. We don't need that entire backend processing. We can also allow non-standard chip sizes, can have several design variants, and it will finally decrease the cost per PIC. So where are we located? We are located in the heart of Berlin. So really in the center in Charlottenburg, having our clean room attached, our backend processing line, and also packaging. Apart from indium phosphide, we're also dealing with thin film lithium niobate, silicon nitride, and the polymer-based platform. So speaking about packaging, that will also come. It's also an important role for RETINA. We can package within a couple of weeks. We do testing in advance. It's followed by packaging. So we do wire bonding, wedge bonding, so we can do that from the DC to RF. And finally, we test the assembly and ship them to our partners, project partners, customers. For LiDAR applications, so we have in RETINA several requirements. So there's a short-range LiDAR used for the healthcare, also for the agriculture use case. We have the long-range LiDAR for the automotive use case and the agriculture use case as well. So there are 3 use cases we have to cope with. And I don't want to go too much into detail about the principle. We've heard it in the previous call, or the previous talk. But the advantage of indium phosphide is that we can put everything on one chip. It's a full on-chip integration. So like lasers, photodetectors, the gratings, everything is on one chip. So, and the substrate we're using is indium phosphide, and it's going to be an FMCW modulation. So maybe in the interest of time, I will skip that slide. I will just briefly point out that there's a tunable lasers used, there are some balance detectors and some photodiodes used at the end of the gratings. So they are just off-the-shelf components being used in that process. And this is the outcome of the first iteration. So on the left-hand side, you find the pig. This is the bearer pig, which comes out of the backend line, and in the center here, you find the assembled pig. It's wire bonded to some ceramics, and then this goes out to the breakout board where you can just easily attach any kind of connectors. Right. So here you can find some detailed photos with the wire bonds, for example. There's the logo of RETINA, designed by University of Vigo. And in this case, we show a long range LIDAR system, and it's a really recent photo, so measurements will follow next. Yeah, we are quite looking forward. So to sum it up, you start, or let's skip the first block here for RETINA, but in general, you start with PIC design. Then we fabricate those wafers within, let's say, four months. Testing will follow, and also the packaging campaign in total consumes about 4 weeks, depending on the complexity. For RETINA, it's quite easy packaging so far. So in the first iteration, because there's no optical coupling needed, there's no RF needed, so it's a really simple packaging, and that's why we can easily scale that up for this first iteration. So to sum it up, we target fully integrated RX and TX LiDAR system, and the first measurements will follow now. So after we ship those modules to University of Vigo, and what we've been showing is that we can offer we are actually offering the entire value chain, so from the die to the prototype package in HHI. So it's like a one-stop shop solution for that project and also for other projects. Yeah. And thank you to the partners, and yeah, especially to Eamon for organizing or for, doing the project management.
Thank you very much, Axel. Thanks, for following up on this topic. And indeed, it's very interesting to see how these kind of LiDAR chips are produced. I'm afraid we need to catch up a little bit on the timing, so I'll just ask you one quick question regarding the light source for both short distance and long distance LiDARs. What are roughly the requirements in terms of power and other aspects? And is indium phosphide really the best platform to do it with?
Well, I can tell you about the powers in general. So like we have lasers in the order of 10 milliwatts at the output of the laser. If it has to travel through the grating, has to be coupled out, there will be definitely some losses. So maybe Francisco can comment on the loss budget or power budget a bit more detailed. But we are quite limited in regard of the power. So we cannot scale it up to 50 or 100 milliwatts per laser. Let's clamp it at 10 milliwatt.
But the question is more from the point of view of the application. Do you think this will be enough power to reach the goals of each of those applications?
Yes, according to our, I'm sorry, Axel, just to jumping in. According to our simulations, our tightest specification is 140 meters. So we needed to reach that. And according to our simulation, we would need like 20 milliwatts power out. And the technology of HHI, the lasers, they can at least emit, let's say, between 10 to 15 watts inside of the chip, not outside, inside the chip. And then we can amplify that because the technology also allows to add amplifiers, so we can amplify that to 20. So that's the expectation. So the technology is very flexible, and
Okay, so SOA is the answer. All right.
So is the
Okay.
answer,
Well,
yes.
good. Okay. Thank you very much, Francisco and Axel, of course, for this presentation. And we follow up with another technology that is in the heart of Retina project. And Carolina Blanche Perez del Notario, a research engineer from IMEC, will help us understand more about these hyperspectral imagers and shortwave infrared cameras. Welcome,
Thank you.
Carolina.
Thank you, Ivan. So I guess you can see the slides already. So I'll try to catch up in time. So first, a quick word about IMEC. So it's a research and development center focused around semiconductors, nanoelectronics, and digital technology. You can see here that image is actually the 300 millimeter clean room, and basically it's because of our clean room infrastructures that we can do all these spectral developments. So this was introduced, the concept of hyperspectral imaging, by Julio. So very quick, just to say, indeed, instead of the 3 broad bands of color, we subdivide into many multiple narrow bands. And then per pixel, we have that, the spectral profile, how the light is absorbed or transmitted, for example, as a function of the wavelength. And this is what provides more discrimination value, much more than a regular color imaging. So what does IMEC specifically do? So actually hyperspectral imaging has been existing for a long time, but what prevented its adoption by industry or many use cases was that the cameras were more based on optical components that were complex and made the cameras more bulky and expensive. So what IMEC is doing, because of the clean room infrastructure, is actually doing spectral filter deposition at wafer level. And then it can decide on the patterning on exactly the number of wavelengths, a type of wavelengths at pixel level. So this actually allows us to have sensors and cameras that are much miniaturized, robust, scalable, because scales with a number of wafers, and allows to have also what we were talking about, that snapshot spectral acquisition, that is trading of spectral and spatial information. Basically, we can do video acquisition. So this can target all kind of dynamic applications, like when we were talking, for example, of real-time surgery. And this allows also, you can see here an example of a nice photon focus and Ximia's very compact cameras. So we have other types of cameras also because of this spectral patterning. And I will just mention quickly, these are more for high spectral and spatial resolution. So typically this is line scan. So every band, let's say every couple of lines correspond to some bands. We have in the visual, near infrared, and SWIR ranges. So these are, with many bands, these require more static imaging, but they are used typically to understand which are the relevant bands for a specific application. So actually here, so traditional ones are more line scans, so they require actually either a conveyor belt or a translational movement, but ours here is has a stage inside that allows moving the sensor and then doesn't require this translational movement. So it can be a static object, which makes it easier, for example, if we were going to do for some initial measurements, for example, at a viticulture case or medical, etc. Then, of course, once we have from this set of 100, 150 bands of line scan, we actually can do an analysis and see which are the relevant bands. Actually, for the snapshot cameras, where as I said, so it's more multispectral. So then you go for 9 to 25 bands. You have them in a kind of mosaic pattern, for example, 4x4 or 5x5 in the case of a visual and near infrared. Then what is then achieved is that we can have imaging of all those bands simultaneously, because basically that the space in the sensor is shared for all of them. So in this project, what we are doing is a sensor upgrade. We are working on that to achieve higher SNR and spatial resolution. So more details will come later on in the project. An example of the also a snapshot when in SWIR, and this is the one that is integrated in the medical case, is the our snapshot sensor with 9 bands, 3x3. Maybe also interesting to say, because it was mentioned, is that you can see here on the right a gap exactly around 1,550 nanometers of the LIDAR, so they're guaranteeing that there will be no interference. And here on the lower part, you can see the 9 bands, how that is captured automatically in one shot and at video rate, okay, for this multispectral sensor. So then also we have other technologies. So for example, thin film sensors with quantum dots. Here, the characteristic is that all these thin film layers have a thickness that is lower than the targeted wavelength. And these sensors, they have the advantages mainly that they allow for a higher pixel density, so to go to higher spatial resolutions, because typically sensors in the SWIR range that we were commenting from 1,100 to 1,700 nanometers, the spatial resolution is more limited, typically for all InGaAs sensors. So this would allow going to higher spatial resolution and would also allow lower cost manufacturing than InGaAs. So maybe here to show, so typically what is done is that we have different materials to play in that stack of thin films, and depending on the choice of the materials, there can be a central, a different central wavelength. That is the sensor responding for. So for example, we have there already like sensors for center around 1,450 or 1,550 nanometers. And then of course, there are many also parameters in this stack of thin films that can be modified to push up the quantum efficiency in some of these peaks. And then specifically for each application, so we will see if there are some wavelengths that are more relevant, and those will be are the ones being feedback into our team of quantum dots to produce some new sample sensors around those relevant targets, relevant wavelengths. So of course, this sensor has to be tested inside a camera. We have a prototype camera that is modular that allows very easily to exchange different sensors of different wavelengths. So far, we have these baselines of lead sulfide of around 1,400, 1,200, and 1,550. We're also exploring other materials that avoid the use of lead for better sustainability. And here you can see an example of an image. So actually, we also have, of course, different types of sensors with different pitch. So with 5 microns at the baseline, but then there are other alternatives we have with higher, allowing this higher spatial resolution. And here you can have an example of an image where you see that this can resolve fine spatial features. This is a quick example just to show how sometimes just, even if we have, of course, hyperspectral cameras, for some specific applications, just the use of one band, even as a broad band, can be useful. So this is a toy example, never better said. Color camera we see on the left with 2, for example, blocks. Black blocks, actually, they have different material. They look the same for color cameras, but for the 1,200 nanometer camera, you see a big difference between the 2 materials. Similarly, typically, for example, clothes are a lot more reflective around this 1,200 nanometers. So you could think, for example, also of automotive and many other applications, where here just one broadband can be interesting. Then what's coming next, also in the quantum dot sensors, is that, as I say, those sensors are centered around one broad peak. But of course, sometimes it would be nice to have a couple of those bands in the sensor. So some very recent work is actually working with meta surfaces here underneath this stack of thin films. And that enables to change at pixel level to move this peak. So the fixed peak, let's say, would be defined by the stack of materials, and then that meta surface would allow some peak adjustments, so changing per pixel. So this is a FAB-compatible process, and there's no need for filters on this fragile stack of thin films, or let's say, or modifying that whole stack per pixel. That would be more complex. This is still, of course, a bit of more complexity in fabrication, but not as complex, let's say, as modifying the whole stack. So there is some already a SPIE paper last year starting to talk about this concept, and actually it's in 2 weeks, start of 1 week, there's coming a publication also at IEDM about this, the advances, recent advances here. So then just to show application for the viticulture case. So Julio mentioned there is one case that is, for example, yield estimation, that is looking at the berries, has to detect the berries versus leaves. And another one is the water content, the hydric stress. So here we try to mimic that, okay, with berries of different colors. So for example, when the berries are more immature, more greenish, that can be more challenging for color imaging. And there's some leaves that have different degree of moisture, let's say. So with this hyperspectral image, so this one is with 100 bands, and you can see there nicely the difference, the classified image based on how dry, or like if it's fresh or very dry, it detects nicely these variations over the image. But actually, if I show the same image with these two well-selected bands, you can get the same kind of information. So then, of course, knowing which of these bands are the most relevant, this allows us to then produce quantum dot sensors with actually specific target bands. Actually, in this study, we also saw that even with one broadband, that is feasible even to target some of these applications. So that was just to show this. And then just as a conclusion, that indeed, so even if you can do the study with many hundred bands, typically a few well-selected spectral wavelengths can be sufficient to target application requirements. And with the technological know-how at IMEC that allows us to customize spectral sensor development, we can specifically target these wavelengths that are targeted in patterns that we select for the number of wavelengths or specific wavelengths we want. Similarly with the quantum dot sensors, as I mentioned. And this kind of sensors that we are developing, they will be evaluated in the viticulture and medical application cases of retina. So thank you very much. For questions, you can address Wouter, Charlie, our program manager, or myself, and for thin film quantum dot imagers, Paweł Malinowski is the main contact in IMEC. Thank you.
Okay, thank you very much, Carolina. Very well summarized. So thanks for also being on time with it. And you had a lot of technologies to cover with. Some of them very disruptive, like the quantum dot sensors, of course. So I wonder if there are any questions from the audience. And in the meantime, I'll actually make the call for the audience in order to contact Carolina if you have another interesting application for such quantum dot image sensors, and also if you can help in their development, because I know there is, of course, a lot of material analysis and that is important in the quantum dot development. Is there anything else, maybe, Carolina, that IMEC could benefit from other companies and other partners that are here?
Well, indeed, apart from end users that need specific applications, I think it's always interesting system integrators, like, for example, Quest is doing the system integration, right? But from the viticulture case, for example, from having a kind of prototype to really having an autonomous vehicle that moves with a nice screen that makes it much easier for the end user, that's always a part that is very interesting to cover with other partners.
Okay. Yeah. So following this call, don't hesitate to contact Carolina and her partners at IMEC. And we thank her again, and we'll move to the last speaker of our workshop today, Peter Mario Schweider, the CTO of Photon Focus, company in Switzerland that is specialized on cameras. And Peter will tell us about the UVV's short-wave infrared HSI applications used inside retina. Right, Peter?
Yes, I hope my slides are seen.
Yes, you're good to go.
Okay. Thank you very much for the invitation and introduction, Ivan. I want to focus a bit on the basics. We heard from Carolina all about the new sensors, and I want to show you why it's so important in hyperspectral imaging and what are the users are looking for. And from all this, we have also some requirements for sensors and cameras. And I will show you how to implement some of these imagers into camera platforms. A short introduction to physics. Hyperspectral imaging covers mostly the spectroscopy which is caused by vibrational effects, vibration and rotations, and it has to be distinguished by fluorescence or phosphorescence, where you have excited states. So we have here we deal mostly with the vibrational energy levels. And most interesting would be the fundamental transition in molecules, but this is in the range of 3 to 5 micron, where the sensor technology is very high price. In fact, nobody works with hyperspectral imaging really in mid-wave infrared. So most of the people concentrating on the first and second overtone covering this by the sphere spectrum. We will later look in the next slide on this, and also there are some applications with the third overtone where we have then possibility to probe the system with visible and near infrared line. So as in retina, we concentrate on the two spectral imaging or two spectral ranges, the shortwave infrared and the visible near. And what could be done with this, as I pointed out already, the fundamental bands are not possible, or they are possible, but nobody can pay in industry for this. At the moment, the current state of the art is of the people focusing with standard indium gallium arsenide sensors in the range of 900 to 1,700 nanometers on the second overtone region and covering a little bit the first overtone. And this gives a lot of issues in, for instance, plastic sorting, etc. You want to have more more extended sphere range. So a lot of work is now done on the indium gallium arsenide sensors to shift the spectrum into the red. And there are several sensors available now which cover these ranges for push broom applications, etc. Besides this, as Carolina showed already, there is a wide range of work to quantum dot sensors ranging from 700 to 2.6 micron. But this is really early stage, and the quantum efficiencies in this sensors, they are not so high as in indium gallium arsenide. Indium gallium arsenide, you have mostly 80% quantum efficiency. If you look at quantum dots, you have some bands, as we saw before, but often the quantum efficiency is 10 or 15%. So this is really an issue, and spectroscopy ends not only with the sensors, you have also to consider the illumination, and it's getting really hard to have a good illumination in all this infrared spectral regions. Nevertheless, I think it's very interesting to focus on the sphere region, but you see also with silicon sensors which are enhanced for near infrared, it's possible to look at the third overtone region, not completely, but mostly, and there are many applications which could be covered. I put here in the bottom line also water, so you see also applications where you're looking for water in leaves or on textiles or wood or whatever. You have also possibilities to detect the water in the visible near range. How hyperspectral imaging applications are realized in the machine vision and in the laboratory. There are several approaches to do this. In industry at the moment, the most common way to make hyperspectral imaging systems are push broom setups. So this is similar to line scan. We here in Retina, we concentrate on sensors with mosaic filters. So with the snapshot enables imaging or hyperspectral systems with more compact optics, and also the integration would be higher. In fact, there are other application or approaches using several sensors with beam splitters and filters, etc. And in medical application and in a laboratory, you have often also application with filter wheels. So there are very special filters then which are moved by a motor head before the camera. What requirements are for HSI? And for HSI, you have two possibilities. You can make it qualitative and quantitative. Qualitative means that you can sort something. Yeah, and if you make a quantity, then you can determine the content of the material in your environment. And if you want to make really quantitative analysis, you need a high signal-to-noise ratio, and this is coming with a high full well capacity. So most of the indium gallium arsenide image sensors, and also the recently developed quantum dot readout stages for hyperspectral imaging, they have a high full well capacity to enable also quantitative analysis. If you work in sphere, often cooling is an issue. So the sensors have to be cooled, and this is not a good idea to have a high power electronics besides this. And it's also well known that heat and optics and metrology are not a good combination. So what we develop in the framework of RETINA is ultra low power electronics for the spectral sensors. Besides this, we have also active cooling with thermoelectric cooling. And here is special that you have often some drawbacks from the cooling electronics to the electronic signals. So it's not so easy to make effective and very stable cooling electronics. Besides this, the customers are interested in OEM stacks, so they don't want to have cameras. Most of the implementations going into spectrometers or setups, and so Photon Focus is specialized to deliver OEM solutions to these customers. And end of the day, you want to have the data in the PC. So you need a very easy to implement data interface. Here we use mostly GigiVision Genicam, which is well used international standard. Another very important requirement from the customer side is the interfacing. So you have a triggered application, you have global shutter sensors, and you have to synchronize the movement of the conveyor belt with the goods to your image grabbing process. So we have an advanced I/O interface to synchronize the cameras to the processes. And nevertheless, you can imagine if you are using cameras in harsh environments, you need robust housings, shock vibration, extended AMI, and all these points have to be covered by the design. As an example, I show you our MV3 platform. This is dedicated mostly for sphere sensor. So we have there the possibility to cool the sensors. And as you see, we have several options to cover the spectrum from visible near to extended sphere. And you see here a very complicated interface where we have an adaptation possible adaptation by software, so we can adapt the shaft encoder interface to all the common standards. We have inside an PID controller for the tech, so we can really stabilize the temperature of the tech very accurately, so that no drifts in the performance of the camera have to be expected. Besides this, we do a lot of pre-processing. Often in spectroscopic or imaging systems, there are some artifacts by the optics, and we correct this optical artifacts by pre-processing in real time in the FPGAs. And for adjustments and for corrections and calibrations, we have also optical shutters, mechanical shutters inside the cameras to enable inline calibration of the cameras. For Retina, we will mostly use our MV4 platform. It's a digital platform with even higher transfer rates, so we can cover their 10 gigabit Ethernet. And the next generation veneer sensor, which is coming from IMEC, needs this bandwidth, and this will implement it in the 60 by 60 millimeter form factor. Good. I think as an example for a custom implementation, I have here a slide from the former project, Multiple, where we implemented 2 of the IMEC sensors in the same package. So in principle, we can handle all the sensors from IMEC to implement stacks, camera stacks, which could be used by the end customer in the systems. So, thanks.
Thank you very much, Peter. Yeah, very exciting domain, of course, you're working with, and yeah, it's great to have you partnering with IMEC and combining, the expertise in the camera development and the image sensor development. So I'm afraid we're quite short on time, and I'll just allow to ask you one question that comes from the audience, from Nikolai from N-Optics. He was wondering, I think, regarding our medical applications, if it's really needed to use the in-gas cameras for this kind of application, or the SWIR detector such as Sony IMX993 could also do the job.
Question to me.
Yeah, it's question to you.
Oh, yeah, okay. Yeah. The Sony sensors are also on the market. In fact, there is an issue, or there seems to be an issue, that there's a too high noise floor. So many of our customers could not use this sensors, and I think in the future there will be a redesign of the sensor. So at the moment it's not, let's say, it's a nice sensor. It has a much lower pitch than the standard indium gallium arsenide sensors available on the market, but there's really an issue with the noise floor. And the other issue is that the full well capacity is really low.
Mm-hmm. Okay, I see. So just briefly, from your perspective, this the project of Retina, does it have the potential to bring also the new type of camera or the new image sensor on the market, and being the the smoking gun proof that these kind of image sensors can be useful for various applications.
Yeah, I think for the visible near, we will have really a new solution, which is based on the experience we had with the sensors before. So this will be really enhanced. And I'm pretty sure that we will find there very nice solutions which cover this third overtone region. And I agree with Carolina. If you know what spectrum you want to elaborate and where you want to dig the data, then you can tweak the quantum dots and push this there. So in fact, I think it's common not to use the wide spectrum for the analysis. Mostly you go on very characteristic bands or spots, and if you know what you are doing, then you can tune your illumination and your quantum dots sensor for this.
Okay.
And then you hopefully can benefit from the much better price performance, price performance ratio.
Okay. Yeah. So I hope you're right about this, and looking forward to see these cameras proving their potential. Okay, thank you very much, Peter, again for your presentation. Yes. And I'll just say a few words to wrap up our workshop. So this was the Retina in Action Smart Photonic Sensing for Healthcare, Automotive, and Agriculture workshop for you. So this explained to you, I hope, in very precise details the work of these 13 partners all across Europe that make this project possible. And among them, I'd like to thank our speakers again of the session today. So Julio, Rick, Dan, Francisco, Axel, Carolina, and Peter. Thank you very much again for showing us a bit of your work and making this workshop so useful. So thank you very much, and please stay tuned with our Retina project to see the future outcomes and the first results coming soon. Thank you very much, and have a good rest of the day, everyone.
Thank you.
Thank you.
Thank you. Bye.
Thank you. Bye-bye.